Hello, Chapel implementers and users workshop attendees. Thank you for coming to the talk. My name is Ben McDonald, and this summer I was the intern for the Chapel team. And I just graduated from Gonzaga University in Spokane, Washington, which is where I am now. And I will be starting full-time with the Chapel team at HPE this July. And today I'm going to talk a little bit about the performance improvements that Elliot Ronahan and I made to the Arkouda set operations over the summer, and also a little bit about my experience using Chapel for the first time. Okay, so just for a quick overview, this talk is going to first give a bit of background information, explaining set operations, NumPy, and Arkouda at a very high level. And after that, I'll talk about the design of Arkouda and how it works behind the scenes internally, which should help make sense of the next part of the talk, which goes over the process and steps that we went through to optimize these set operations. And finally, I'll show some performance results and draw some conclusions from these results to wrap up the talk. Okay, so to understand what it was that we were trying to optimize, here's a little bit about what set operations are and what they can be used for. So set operations are something that you might have learned about in a discrete math class, and they allow interactions between two sets or arrays with the goal of getting some information about the items contained in the sets, such as what items are in one set but not the other, or the combination of the two sets, and pretty much just every way you can think to compare two sets, there's a set operation for it. So yeah, and these are commonly used operations within Arkouda and data science in general. And they have many uses, like understanding the physics of a data set or generating interesting graphs, for example. And the frequency that these set operations are used is why set operations made a good candidate for optimizations in this project. So the picture on the right here, this shows the 4 set operations supported in Arkouda being called and what the result of those function calls are, just to see some set operation results. And also this picture shows the process of connecting to and using Arkouda. And that's what those 2 first lines are, which could be interesting if you haven't seen that before. Okay, so to understand Arkouda and these changes, it's important to at least be familiar with NumPy and data science first. So before getting into Arkouda, here's just a quick overview of NumPy and data science. So NumPy is a widely used Python package with an assortment of routines for fast operations on arrays. And NumPy is able to accomplish this fast performance by using pre-compiled C code that the Python code calls into. So you're not really using Python code in NumPy. And so NumPy is very popular in data science, and at a very high level, data science is basically just trying to understand a data set in human terms through all kinds of things, such as statistics and trends that can be found in the data set. And the way this is generally accomplished for a data scientist is loading in a data set into memory and then manipulating that data set, doing all kinds of things to try and draw out what's going on in that data set and really understand what the data set can tell you. And so, of course, NumPy has a lot of good things about it, but utilizing supercomputers for data science tasks in an efficient way is not NumPy's specialty, since NumPy is written all serially. And this is not just a problem with NumPy, but it's a problem that is getting more and more important in data science as data sets are growing larger and larger, with people now accumulating tons of data on pretty much everything that goes on online. And so that is where Arkouda comes in. So Arkouda is an open source Python package that is implemented using a combination of a scalable Chapel server that performs the computations and a user-facing Python client with a usability very familiar to NumPy. So Arkouda enables interactive supercomputing for data science in a way that doesn't require learning what is basically an entirely different field of HPC and HPC programming. And beyond that, I would like to add that Arkouda is able to interoperate with NumPy and utilize some of the great features that have already been developed in NumPy that don't require a supercomputer, such as histograms, for example. And so typically how Arkouda is run is by starting up an Arkouda server in a terminal, whether that be on your laptop or more likely a supercomputer, and then connecting to that server in Python through a Python 3 client with something like a Jupyter Labs notebook, for example. And so here's a diagram explaining Arkouda's design at a very basic level, in case it hasn't been clear so far. And so Arkouda is run with a backend using a Chapel server that can be run anywhere from a laptop to a supercomputer. And then a user, or I guess even many users would connect to that supercomputer from their laptop running the Arkouda server and be able to get results viewable locally from a message that the server would communicate back to the user's Jupyter Labs notebook, for example. So basically, what Arkouda does is allow a user on their laptop to process their data in Python like they always do, and not even think about how it is being run on a supercomputer. And the value here is that nothing new has to be learned for a data scientist. Data scientists can just keep doing data science like they always have, but now they can just work with much, much larger data sets. All right, so now getting into the performance improvements that we worked on for the set operations in Arkouda. So previously, these set operations were written purely on the client or Python side of Arkouda, which is one of the advantages of Arkouda, showing that a Python programmer can write parallel distributed code in Python using Arkouda without having to touch anything in the server and only writing Python code. So the only problem with this approach is that it can cause a lot of server communication, which was the case for the set operations because they used many slices to perform their computation. And each one of these slices requires its own server call based on how Arkouda is implemented. And this was essentially wasting performance on time not spent actually computing the result of the operation, which is something that's very noticeable for something used as frequently as set operations. And so this is the problem that we set out to fix in this in this optimization, where the goal was to move these set operations to purely server-side methods, where they would only require a single message of communication to be sent from the server to the client, where previously a single set operation was using about 10 messages each. So 10 communications to the server was taking up a lot of time previously. And so the final result of this effort was performance improvements to the set operations ranging from about a 10% increase all the way up to around a 90% increase in the best case. Okay, so just to highlight briefly what this work actually entailed, here I have a code snippet of intersect, which is one of the Arkouda set operations that were optimized to these changes. On the left, you can see the Python code, and on the right, you can see the Chapel code. And basically the process in this optimization was to take the code written in Python and convert it to Chapel code, moving it directly into the server. An additional benefit besides cutting down communication that came from moving these operations to the server side was we were able to have more control than is offered by Python, and we were able to really get every drop of performance out of these operations that was possible. And I think I mentioned this at the beginning of the talk, but this project was my first time ever working with Chapel. And as you can see, the Chapel code is quite comparable to the Python code in terms of number of lines as well as readability. And that definitely was good news for me. And I think that says a lot about the high level, easy to understand syntax of Chapel that makes the experience much more positive than it can be with some other languages specifically ones dealing with parallel and distributed programming when you're just getting started with that. So also using Chapel helped me to learn and understand parallel and distributed concepts through getting hands-on practice with them without needing to be taught them in advance. And I definitely prefer this to reading a textbook, and I think it helps just grasp the concepts. And I think that's something that is unique to the Chapel language. Okay, so here are the benchmarking performance results that run on the set operations nightly in Arkouda. And that large jump that can be seen is where these optimizations were merged into the release branch of Arkouda. And the table underneath the graph, this shows the actual performance numbers in gigabytes per second with a percentage speed up column and a before and after columns, before and after columns as well. And as you can see, Intersect was the top performer, improving about 90% with our changes, and Union and XOR saw similar comparable results to this 90% number, while the set difference experienced more modest improvements with about a 10% increase. And the reason we're seeing a smaller change in the set difference is due to the benchmark, that the actual benchmark test that we use to collect these performance results. And in practice, the set difference will actually see much more comparable performance improvements as the other ones. And so that concludes the set operations optimization work. And so in conclusion, while moving the set operations to the server side operations improved performance pretty significantly, as you saw. I don't want the takeaway of this talk to be that everything in Arkouda should be written on the server side, because too much of that would kind of get rid of some of the value of Arkouda. And one of the really cool things about Arkouda is that a Python programmer or a data scientist doesn't need to know anything about parallel distributed systems to write parallel distributed code that runs performantly on terabytes of data. And I'm not arguing that against that. I'm not saying Arkouda should, think about more of just a server model, but instead, I think a more valuable takeaway from this talk is not to look at this approach to optimization as the answer to all of Arkouda's potential places to improve performance, but I think it just highlights some areas that could be improved in Arkouda and gives us some value data points for understanding the effect that this communication has on performance in Arkouda. And also, I think while it could be valuable as an Arkouda server developer to keep in mind the server call slowdown when implementing new features, I think what's even more important to remember is the goal of Arkouda, which is to enable data scientists to interactively use supercomputers for data science tasks. And what that means is keeping the flexibility in the hands of the client-side user and not trying to do everything on the server just for a little bit of performance improvement. And I don't think that thinking is really a concern for the core developers of Arkouda, but it wasn't something that was immediately clear to me. And I think it was a good lesson learned from this project. So lastly, I just wanted to say thank you to the Chapel team, specifically Brad, Engin, and Elliot. Even though Chapel helps make parallel programming easier, I still needed a lot of help along the way. And I was really grateful to be on such a helpful team. So thank you guys. And also thank you to the Arkouda team, specifically Mike Merrill, who put up with all my questions and helped to improve my code a lot and getting that into the main branch of Arkouda. So yes, thank you Chapel team, and thank you Arkouda team as well. All right, so thank you all for coming. And it was unfortunate I couldn't attend True Live this year, but any questions are in good hands with Elliot here live for me. And with that, I will now direct any questions that you may have to Elliot. So thank you, everybody. Bye.